All right, let's start this recording. Happy Friday. You did it. Just like that, it's already Friday. So I didn't write it down in our class, but I wrote it down after because we were doing a hypothesis test for, what was it about? Oh, Jocko's Garage, that scoundrel. Let's see here. So we wanted to know if Jocko's estimates were significantly higher than the trusted garage. And so then we have paired data. So we introduced this idea of a special case of two samples, but now they're paired, right? And so then we analyze the differences. But once we have the differences, we just have one sample of differences. And so then we're back to the one sample mean type of strategies, right? And the conditions stay the same, right? We need to be able to assume that the observations or each of the differences is independent of the others, okay? And normality hinges on the sample size, right? If the sample size is less than 30, then you have to make sure that there are no outliers. If it's greater than 30, then you can handle outliers, but no extreme outliers. Okay, so which are like crazy extreme outliers. But usually we can just go ahead and assume normality if the sample size is larger than 30, okay? Which is a huge selling feature of the t-test. Okay? For our null hypothesis for paired data, what's nice is that this is always your null hypothesis for paired data, that the mean of the differences is 0, right? Which means that the null value is 0. And then the tricky part is figuring out what the sign is for the alternative hypothesis, right? We had to do a little bit of work saying, okay, if I calculated the differences this way, j minus t, and I want to know if j is greater than t, then j minus t must be greater than 0. So there's a little bit of kind of work went into this sign here. Okay. And then we calculated our t, and then we used the table to find the p-value at 9 degrees of freedom. And we had a one-sided test. And so our p-value is somewhere between 0.005 and 0.01. Then I let you guys go and I said, oh, I'll put the conclusion into the notes, which I did. So just the same as always, right? Since the one-sided p-value is between 0.005 and 0.01, it is less than the assumed alpha level of 0.05. So it wasn't given, so I assume it's 0.05, which means we have enough evidence to reject H naught in favor of HA. Remembering your conclusion is always in terms of, can you reject H naught or can you not reject H naught, right? This means there is evidence that Jocko's estimates are significantly higher than the estimates. I don't know why I put a question mark here. It doesn't make sense. From the trusted garage, exclamation mark. How about that? I think I just copied and pasted the question and I wasn't thinking. And then I snuck this in there. Might not have seen it, but for today, so, okay, so the estimates are higher. How much higher, right? Oh, these are from the notes posted from yesterday, yeah. Just give yourself a good 10 lines or so. You're good. Because, so now, last day, we found Jocko's estimates are significantly higher than the trusted garage, right? Are significantly higher than the trusted garage. I'll capitalize the trusted. It's not the name, but I don't know. Maybe I shouldn't. It's weird. Oh, right with my eraser. Trusted garage. How much higher? To answer this, we're going to need a confidence interval. Okay. And so that's the relationship between hypothesis testing and confidence intervals is, okay, a hypothesis test tells me that, yeah, there's something going on here. And then if there is something going on, usually we follow it up with a confidence interval and say, oh, and here is exactly what we think is going on, right? And so need a confidence interval to answer this. So we still have paired data, and we know the confidence interval, although the formula is the same. I've just, wait, why is it? It wants to have the, don't want this here. Oh, I'm doing stuff in secret here. You can't see it. Sneaky, sneaky. There, which is actually good for me to know. Then I can do a bunch of weird stuff in there. All right, so this is the same formula that we had before. It's just that it's emphasizing that we're talking about the differences, right? So the mean of the differences, the standard deviation of the differences, and the number of differences. And then the T star, so the critical value still has n-1 degrees of freedom, where n is the number of differences, right? And so here we go. Construct a 95% confidence interval for the true difference, right? Because we're talking about, it's a confidence interval for the population mean difference. Okay, so for the true difference in estimates is what we want to do. So we need T star. And T star, so we need T star at n diff -1 degrees of freedom, which is T diff, or a T star of 9 degrees of freedom, because we had 9 cars for a 95% confidence interval. Can grab this part. Nine degrees of freedom still, and 95% confidence interval. So then my T star is 2.262. All right, everything else we already had, and that's not even that much work. So here we go. So X bar of the differences plus minus, oops, Z star, T star at 9 degrees of freedom. You can drop the degrees of freedom subscript. It's just meant as a reminder. Okay. S diff over the square root of N diff. If I remember, and I have cheat sheet here. I did not remember. Okay, that's okay. 80 plus minus 2.262 times the standard deviation, which we were given was 84.59052 divided by the square root of 10. Because of how I did it before, I have slightly more decimal places, so I'm just gonna do this in here. Oops, clear all. All right. I am going to find the margin of error first. First, the standard error, 84.59052 divided by the square, oops, not the nth root, the square root of 10. Okay. Great. Then 2.262 times that previous answer. Okay, that checks out. And then here, I'm just going to label this ME, so the margin of error, because then I can do kind of fun things. I know I'm kind of, it's a little bit rude here, or maybe I'll just call it M. I think it's complaining. When we were working online, you could use a nice calculator like this where you can store values, but a lot of calculators have a store function, which I would encourage you to learn how to use and use, because then you can keep all your decimal places. So that's nice. All right, so then the lower bound is 80 minus that margin of error. Yes, checks out. And the upper bound is 80 plus M. And that matches as well. Can you believe my luck? I'm going to screenshot this and bring it in. So then my interval, remember this is a difference in money, so I'm going to round it to 2 decimal places. Sorry, they're super tiny. 1949 and $140.51. Quite a large range, right? But that's because of this huge standard deviation, right? So it's somewhere between, oops, I'll use a dollar sign, 1949 and 140.51. We can still interpret this interval just the same way that we've been doing. Just remember that you're talking about the difference, right? And how we found the difference was Jocko's minus the trusted garage. So this, right, if we wanted to show off a little bit, right, Jocko's estimates, so we're 95% confident that Jocko's estimates are between 1949 and 140 and 51 pennies, higher than the trusted garage. Or you can just talk about the difference. That's safe too, right? That's still true, just depends on how comfortable you are with the interpretation. So, but same blurb as always, we are 95% confident. The interval from 1949 to 140 and 51 pennies captures the true, and how did I say it? True difference in estimates. Or we're 95% confident that Jocko's estimates are between 1949 and 140.51 higher than the trusted garage. 95% confident. Jocko's estimates are between 1949 and 140.51, 51 pennies higher, hopefully it makes sense, than the trusted garage. when you're first starting with these questions, because it can be kind of difficult, right? You can just talk about the true difference as long as you're talking about the difference, right? Because we analyze the mean of the differences, or maybe I should even say mean difference in estimates. Right. Probably. But it wasn't in the question, so I don't expect you to be fancier than how I've worded the question. I expect you to just take the question and reword it as an answer. Okay. But how about for the true mean difference? That's better. I should have had that. All right. Awesome. Oh, Emily, can't you show us another type of question? I know, right? How about 2 independent samples? So I've managed to finally sort out the coding for the questions. So now they're hopefully working. And I posted an assignment for 1 sample means, but I'll also post one for 2 sample means so you can work on it. But it's not done yet. But here we go anyways. Any questions before we start the next section? Start it on a fresh page. Nope, just keep going. Difference of 2 means. I usually call it 2 independent sample means. And so here, sometimes I call it 2 independent sample means. Just to emphasize that, okay, unlike the paired data, now if I just have 2 different groups and I want to compare their means, then of course there's no way to link the 2, and that's okay, right? We can compare the mean of group A and the mean of group B, and we're allowed to do that, and then we'll have tools to do that. Okay. And like I was saying, t-test is super common, but this is probably the most common one that you're doing, right? The mean return of fund A versus fund B, right? They're not linked on anything, maybe the day, but overall, right? And so now I like to throw in the independent just as an emphasis. And let's jump straight to the formula sheet here. So we move down, and by now, right, we can kind of take a step back and have a look at this, and we're able to do pretty much everything with just this information. You might not feel like it, but you can, okay? I always say it's kind of like Sound of Music. When you know the notes to sing, you can sing most anything. Thank you. And that's the first time someone sang along, actually. So thank you. Right? But if you know what the point estimate is, if you know the structure of the confidence interval and the standard error of the point estimate, you know the critical value, you know the setup for the null. Oi, it's gone. It didn't like it. Hey. You know the setup for the null and alternative hypothesis. I tell you how to calculate the test statistic, and it's a T, which you know how it works. And I tell you what the degrees of freedom are because it's a T distribution, so you'll need that, right? You can do all these problems, right? And so that's kind of fun, right? Took us time to get here, took us a lot of practice, right? But that's the really fun part about hypothesis testing. and you thought there were none. Paste image. Okay. So I start off and I give you the sampling distribution of the difference of the two means, right? Which is, of course, how we're going to compare these two sample means is, okay, well, what's my best guess at the difference in the two sample or the two population means? Well, it's the difference in the sample means. Yeah. So here, the point estimate is going to be x1 bar minus x2 bar. We've seen this setup before with the difference in proportions, and yeah, it's going to be very, very similar, right? The problem, not the problem, but the reason the formulas look so big is because now each sample has a mean, each sample has a standard deviation, each sample has a sample size, and they're not necessarily the same. So that's kind of fun. And so the point estimate is going to be x1 bar minus x2 bar. And the standard error of the point estimate is going to be s1 squared over n1 plus s2 squared over n2 square rooted. Unlike proportions, notice that the confidence interval and the hypothesis test use the same standard error. So you don't have to switch back and forth, right? And so that's nice. What was the problem when we had a proportion question? So a two sample proportion question, we had to use the pooled proportion and it had like some added work, like, can't believe I said that. So hopefully I never say like, I don't know why it came out. I don't, because it jars me. All right, so the standard error is the same. Okay, and so if I get you to do a hypothesis test, it's not that big of an ask to get you to do a confidence interval as well, right, as a follow-up question, because you can just take the calculation that you did here and use that value here. And even if it's wrong on the quiz, right, if you follow through, then that's okay, right? You're allowed that. I'll follow through and I won't take more marks off or anything. Okay, so where do we want to start? Oh, maybe let's talk about the degrees of freedom. Okay. Software is going to use a more sophisticated calculation, and I wonder if I have it. I don't think I have it anywhere handy. Actually, let me see if I do. Did I keep it here? Did. It's really bad. Okay. So software does this, right? They can do that. We're just going to take a more conservative approach, which is just the smaller sample size minus one. Okay, and so so that's what I want to highlight here. Software does this calculation but when doing stuff by hand, like we do on the quiz and on the final exam, right, you're just going to use a smaller sample size minus one, and bless you. But when doing calculations, you guys know what I mean by hand. Obviously, you can use a calculator, but we use the degrees of freedom is the minimum of n1 minus 1 and n2 minus 1, so the minimum function, but this really is just the smaller sample size minus 1. Phew, right? Okay. But I do get a lot of questions later if you're looking at software output. My degrees of freedom don't match. I know they won't. They can do this relatively easily. It's just the standard deviations and the sample sizes. It's no big deal. All right, but there's a reason it's not on your formula sheet. I don't want you to do it. All right, good. Degrees of freedom, done. The only thing that changes for your conditions is, let's see here. Yes.
Because it said minimum.
Yes.
Whichever value ends up being smaller value.
Yeah, the smaller sample size minus 1.
Okay. And you take
the conditions, we just have one little extension, which we've seen before. Okay. I'll zoom in. We still have the independence condition. It's extended. Okay, so the data are independent within, which is what we've been talking about, but also between the two groups, right? Because these two groups have to be independent of each other. Otherwise, they're paired, right? And so in order to do a two independent samples t-test, right, they have to be independent within and between the two groups. So, which really we can just check by saying that the data come from a random or two random samples usually, or a randomized experiment. And then the normality condition, you're going to check it for both groups, right? Individually, the sample size. Remember, the sample sizes can be different, right? So you want to check it for both. Okay. You can still, in theory, make a histogram of group 1 and a histogram of group 2, and then make sure that they're approximately normal if the sample size is less than 30. Otherwise, if it's 30, you just go for it. Okay. And then, oh yeah, the official formula for the degrees of freedom is quite complex. It is. So we're going to use the smaller of n1 minus 1 or n2 minus 1. Okay. So here, in terms of the conditions, I'm just going to generalize it as check the conditions for each of the two samples, right? For each of the two samples. It's basically what it's saying. Okay. Our confidence interval is about mu1 minus mu2. So it's going to be about the difference of the means as opposed to the mean difference, which is what we were just talking about. So kind of a mind twist there, right? So you want to keep them really straight. So the difference of means and the point estimate for a difference of means is x1 bar minus x2 bar. It doesn't matter which one you make and which one you make group 2, as long as you're consistent, right? And we've seen that before for proportions, two sample proportions, right? Same thing for the null hypothesis or the hypotheses. I'll grab this because I want to talk a little bit more about it. So, or if you prefer to talk about the actual parameter that we're trying to estimate, right? The difference mu1 equals mu2 means that mu1 minus mu2 must be 0, right? So if you prefer to use it this way, that's totally fine, because your hypothesis is technically about mu1 minus mu2. But just like proportions, we're never going to talk about something that's not 0 for the difference. It's so rare that we would care about that. So mu1 minus mu2 is not equal to 0. That's the default, right? But you can have greater than. Because we do all our hypothesis testing, assuming that the null hypothesis is true, right? That simplifies our test statistic, right? And so here, remember, we do all our testing assuming H naught is true. So the T that we have, remembering the general setup, is the point estimate minus the hypothesized value divided by the standard error of the point estimate. That's always been our test statistic, right? Whether it was a Z or a T, it's just that Z are for proportions and T's are for means. So then T is X1 bar minus X2 bar. We said that was our point estimate for mu1 minus mu2. But from here, right, this is equal to 0 from the null hypothesis that mu1 minus mu2 is equal to 0. Even if you use mu1 equals mu2, mu1 minus mu2 is still 0, right? They're the same. So it's not even included on your formula sheet because it would make it look way too big and nasty. I don't think it's included. And then divided by the standard error of the point estimate, which is S1 squared over N1 plus S2 squared over N2. It doesn't look like an extension from the one sample case, but if you kind of look at it, so we used to have S over root N is the standard error for one sample. But if you put it all under the square root, this is the same as S squared over N, right? You can distribute the square root. And so it is more alike than it initially looks, I guess, right? S1 squared over N1, S2 squared over N2. This is where people love to forget these squares, right? It's a big calculation, so you want to make sure that you're really careful when you're adding those squares. So notice, right? And if this part doesn't make sense or doesn't help at all, then just ignore it, right? I just wanted you to see that it's basically the same, except now we have two samples, so two different standard deviations, two different sample sizes, and we need to be able to handle that. And so a star is born. 2 sample t-test. Ta-da. And that's what's on your formula sheet. Right. But I just wanted you to see where it all came from. All right. don't have a ton of time, but I do want to do this example, or at least start it. Give it to you to think about over the weekend. Is there anything better? No, you can think about it Tuesday morning. That's fine too. I think this one's kind of cute because I have definitely done this. So here we go. An instructor decided to run 2 slight variations of the same exam. Prior to passing out the exams, she shuffled the exams together to ensure each student received a random version. Summary statistics for how students performed on these 2 exams are shown here. Anticipating complaints from students who took version B, she would like to evaluate whether the difference observed in the groups is so large that it provides convincing evidence that version B was more difficult on average than version A. Okay. So if you put yourself in this instructor's shoes, are you hoping to reject H0 or fail to reject H0? You're kind of hoping that you can't reject H0, right? That there's not enough evidence to say that version B was harder, right? Because then you can go back to your students, in your face, they're not significantly different or something more subtle, right? So I've done this and there's lots of social experiments where I declare that one test is harder than the other one. And then people do poorly on that one just because they think it's harder. Yeah, Steve always jokes about that because he'll use different colors on the final exam. He jokes and he makes it clear because otherwise it does impact your scores. But he'll say, oh yeah, the green one's a lot harder. They're the same, but yeah. So there's a lot of interesting research about the psychology behind it, right? But also this is how you would test it, right? So you've got these different scores, and again, as soon as you have 2 different standard deviations, that's usually what I latch onto, right? Then I know for sure that this is a 2 independent samples. Independent sample means, I guess, question, type of question. 2 sample means question. And especially if there are different sample sizes. Sometimes I'll give you information like all of this table, but also the difference. And there'll be some number here, number here, number here, number here. If you have the differences, then of course this has to be the same. But then if you have information on the differences, then it's probably going to be a paired data type of question, right? Then A and B are decoys, not decoys. They're used to calculate the differences, but you can ignore them. Whereas if you only have information that looks like this, you want to confirm it by reading the question and just kind of convince yourself that you have 2 independent sample means. But yeah, when it's laid out like this, you know it's a 2 sample means question. Okay. Let's start with the type. Because like I said, on quiz 4 on the final exam, I'm going to make you tell me what the type of question is, right? That's to put you on the right path of your calculations, right? So the type here is 2, and I like to emphasize this with independent sample means. But if you just call it 2 sample means because that's what it's called on your formula sheet, that is fine, right? So then if I've decided that it's a 2 sample means question, then this is the only part of the formula sheet that I can and should be looking at. Right? For any t-test, the conditions are the same, right? So first, we're going to check the conditions. The first one is independence. Let's see here. She shuffled the exams together to ensure each student received a random version, right? So the 2 groups were randomly assigned, right? We also have to assume that the students within each group are also independent of each other. Not necessarily true, but we're going to assume that it is true, right? Students were randomly assigned a test version, and we assume the students are all independent of each other. The students are independent of each other. The second condition is normality, just as before, but we have to check it for both samples. So normality, we were told that the sample size of version A is 30, so just at the cusp, and version B is 27. We also have the minimum and the maximum, so we can go ahead and for outliers on either end. Oh boy. All right, here we go. I'm gonna grab all this information. Since NA and NB are less than or equal to 30, we need to check for outliers. We don't need to check it for version A, but we may as well because we can. We need check for outliers, which is why they have given us the minimum and the maximum. 45, what are we doing? We're just trying to see how many standard deviations minimum is from the mean and how many standard deviations the maximum is from the mean. And so let's see here. Z45, just because otherwise there's a lot of information. So I'm going to use subscript divided by 14. (45 minus 79.4 divided by 14). Negative 2.457. You know what? Let's put this down here. Borderline, but we'll let it slide because the sample size is large enough, right? And it's still not larger than 3 standard deviations away. So 100 minus 79 divided by 14. $1.471. $32 minus 74.1 divided by 20. And aren't you guys going to be so lucky? We'll just finish checking the conditions and then you can work on this problem on your own. We'll finish it next day. Z32 is negative 2.105. And finally, 100 again, but a different mean and standard deviation, 74.1 divided by 20. $1.295. Hopefully I didn't slip up. Ding, 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 ding. All values are within plus minus 3 standard deviations. So we can assume no outliers. So much work. I think it warrants an exclamation mark. So we'll pick this up on Tuesday, but try it, see where you get to. You have all the tools, you can do it. All right, if you have any questions, let me know. Otherwise, I hope you have a great weekend. See you next week. I better stop this recording.